In this lecture, we'll discuss outliers and irregularities. Almost all forms of measured data contain some weird outlier results, strange data points that you just cannot explain for any reason. That might be due to faulty sensors, someone bouncing the sensor, or something just strange happening. And these values will occur as strange outliers. For instance, here I have simulated and added 3 components to this data set that are clearly different from the rest. So these are fairly obvious, and this is the model that I have for the rest of the data set, but you can see those 3 points are quite different from the others. I need to deal with those. If I do not deal with them, I will get very strange results in my estimates, and they might easily corrupt everything for me so that I will get erroneous results. So for instance, here I'm estimating the Tacf and I'm comparing to the true values. The circles here are the true values, and the Tacf estimate you can see here are the ones with stars. And this is without the outliers, and you see that I get very accurate results, which is not surprising. I don't get perfect results because I have a finite amount of data, which is also what you can expect. But at least they make sense that I get something reasonably close. However, if I add the outliers and I re-estimate them again, notice that now instead of getting this value positive, I got it instead negative. And similar for these ones. So my Tacf estimates are clearly corrupted, and this is because of the quadratic form of the estimation here. If I have a cost function that has a quadratic cost term in it, and I have an outlier value, this outlier value will very strongly affect my minimization. It's therefore very important that I start by detecting outliers and then in some sense remove them or deal with them in some other way. And if I cannot do that, I need to have an estimator that is robust and allow for the presence of such outliers. Otherwise, my estimates are not going to be reliable. The easiest thing here is, of course, that since I see them very clearly, I'll just omit those samples and I'll get then a data series with a hole in it like this, which immediately then asks the questions, what should I do when I have a data where I'm missing a data point here? I don't have it. What you typically do is you do linear interpolation. So that means that if I have the points like this and I'm missing this one, I do a linear interpolation between the 2 neighboring points. So I typically draw something like this and recreates the missing point as here. I can also use a spline interpolation so that I use the neighboring points. I can use these points and try to get a spline fit, and then I would use this point instead. There are also other ways. I can use a Kalman filter, that we will discuss later in the class, and use my models. For instance, if I have an ARMA model for my data, and I can use this ARMA model then to be able to reconstruct the missing data. But we'll come back to that when we talk about Kalman filtering. A quite simple way to omit outliers is to sort your data, basically getting them in size order like this. And then what you do is you just omit the very largest values and the very smallest values and sort them back. Of course, this will require quite a bit of bookkeeping, and it will also have the problem that you will have missing data points in your data set that you'll have to deal with in some sense. There is a function Tacf, which is the alpha-trimmed autocorrelation function estimate, which will do exactly this, and then it will reconstruct the Tacf estimate accordingly. And as you can see here in this estimate, this would be the estimate I showed before when you have this clearly erroneous estimate. This is the Tacf estimate, and you can see it is robust to these 3 outliers because they have now been omitted. And of course, when you resort them back, I have lost some data points, so I have fewer data points, but I do not suffer from these very large outlier points, and so therefore I can reconstruct my data well. This also points to another use of the Tacf function. If you are unsure whether you have significant outliers in your data that might affect your data strongly, what you can do is simply to compute both the Tacf and the Tacf and then compare the two. If they differ significantly, like in this case, you clearly have outliers that you need to deal with. However, if the 2 estimates are very similar to each other, your data set has probably not been affected by very strong outliers affecting your estimates pronouncedly, and you can proceed with the Tacf as usual. Here is a currently quite relevant data set. This is the mortality data in the United Kingdom during some recent years. And as you can clearly see, during 2020, there was something strange happening in spring. I wonder what that can have been. What you can see from the data is also that there's some strange effects, that you have serious dips in mortality and then an immediate after following peak of the mortality that happens very frequently in the data set like this. This is a quite common thing that happens in many forms of data sets. This is due to the Christmas. They are not reporting mortalities from the hospitals during Christmas, and then after the holiday, they are reported. So it shows you first a dip because then nobody died, but that is just because nobody was reporting the death. And then after that, you see lots of death because then, of course, then the death that came from the previous days are occurring. You need to deal with this kind of outlier behavior. This is a strange data irregularity that you need to deal with. It's not an erroneous data point as such, but it is an irregularity that is due to the way the data has been reported. This form of irregularities are very common in data sets that are reported by human beings and not automatically by some form of machine. And then there might be work schedule effects that causes some strange behavior in the data that you need to somehow deal with. Ideally, Ideally, what you would do here is, of course, that you would smooth over the data points, such that if this was the Christmas break and then this is the you would take these data points and move them down here, and you would get something similar like this that will cover it well. A simpler way to do this is to use a so-called median filter, where you replace the data points using the median. So imagine that you have your data set like this, and I divide it into small sub-chunks like this. Each of these subvectors has the form of containing a couple of samples, say 3 in this example, that I can then compute the median of. If I take, for example, that I have 2, 4, 1 as my current example, I will replace those with the median, which would be 2, so that this point, the middle value here, be replaced by the 2. In this way, this strange kind of effects will be smoothed out, and I will have something resulting like this instead. Of course, this is not perfect, but it's quite reasonable, and it works very well in most practical applications. So this would be a first thing to try in many applications. Is it good enough? Then you can just stay with that. If it's not good enough, of course, then you will have to do something smarter than that. Maybe build a model to take care of these kind of particular effects. And here, in this case, it would be relatively easy to build such a model, since you know basically what's happening. If I use the median filter, I will get this result, and I do not have then this strange behavior due to the reporting issues of the data set. As you can see in the data, there's a clear annual periodicity in the data. People tend to die in the early spring, and this is true everywhere. The winter has been hard on you, and then you tend to die in the spring. But there is also a growing trend in your data. You can see that there are more and more people dying every year, and this is because of the growing population in the UK. So probably we cannot make the conclusion that this is due to the diet of fish and chips that these people have, but it's rather because there are more people living here. So what we do now is we split the data into 2 data sets. One is the modeling data set, which we will move all the way up to 2018, and then we'll have a validation data set one we'll use for testing the model later on in the course when we come to the prediction part. So let's take this part of the data set and try to see if we can build a model for it. So of course, the first thing I do is I detrend my data by using a nabla operator like this, and then I compute the Tacf, and you can see that there's a clear periodicity of 52, which is not then surprising because you have this annual periodicity. You can also see it in the Tacf, where you have this periodicity of 52. It's interesting to see that I also have something strange going on just before and just after 52, and you might wonder if there is a periodicity of some kind there as well. This is probably due to the first coefficients here affecting in the convolution of the 2 parts. We'll come back to this and see if they're still there or after we add the model. But for now, as you know, we will start modeling the A coefficients first, so I'll add an A52 term into my data set, and I will use that as differentiation and see what I get, and looking at the MA part as the next step. I will therefore begin by adding an A52 term to the dataset, and I re-estimate the Tacf and the Pacf for those. You can see I still have something strange going on here at the higher order lags in the Tacf and the Pacf. I also seem to have something here that seems to indicate that I have differentiated the data too hard, and maybe I should have used an A1 term instead of using the nabla operator as I did. But this is not how you should be thinking about it. Remember, we added an A52 term, so therefore you should move over and look at the Tacf now instead. I want to model the Tacf. I first do the A part. That's what I did. I added a 52 term. Now I have to then look at the C part to see if I can add an MA term to take care of things. Here you see I do have these 52 periodicity here also in the Tacf. That might be a worry, but I also have a strong component here at C1. So I'm thinking maybe I have missed something here in my model, so that I should add my C1, and this result here at the 52 lag is a result of the A52 component not being accurately estimated because the model was not detailed enough. Clearly, if I had an A52 term, but I did not have a C1, I will not have a model that is accurately described, and therefore my estimates are going poor, and I will still have some weird effects going on at around 52. So it is a reasonable assumption to make. However, I'm hoping that by adding the C1, I will remove this effect. Adding the C1, you can see that this is exactly what happened. I now no longer have the periodicities around 52 in my Tacf, and I no longer have anything strange going on here. And the same thing happens for the Pacf, where we'll look at that. And if I look at this autocorrelation function estimate here, this seems to suggest that the data are white. I do have one point here that seems to be just slightly outside, something that is still touching here or something, but this is close enough for us, and we will definitely deem this to be white. And if I try it using the whiteness test that we'll cover later on in the course, this is definitely marked as being a white sequence. So note the importance of re-estimating your parameters when you change your model. This is very important for you to do that, because the previous estimate of the A52 here was clearly wrong, and that will affect my model strongly. If I did not re-estimate it when I added the C1 term, this would have corrupted my model. Later on in the course, we'll test this model on the validation set to see if we can describe also data that we haven't used to build the model, and then we'll try to use it to determine how many people ought to have died if there hadn't been a pandemic.